So in this video, we are going to go through polar form and how to manipulate things and use polar form. And secondly, how to use Demoivres theorem, or at least introduce you to Demoivres theorem. Later on, we're especially going to use Demoivres theorem to basically solve for the roots of an equation. Okay, so we're using powers and things. So I could find the cube root or the fourth root and all of those sort of things, which we'll go into a little bit later. Now this thing, first of all, whenever you have something like this, my advice is you need to sketch an Argand diagram, because each of these things in Cartesian form really need to be converted to polar form. Now I'm just looking over here, 1 minus root 3i. I've got 1 and minus root 3i, so it's sort of over here somewhere. Okay, that's 1 minus root 3i, which is in the fourth quadrant. And minus 1 plus I is over here. Minus 1 plus I is over here in the second quadrant. Now, just so you know, I reckon just from that, you could sort of get an idea. But remember that when we're doing this, what we're going to say is 1 minus root 3i, that is equal to something in polar. That's equal to, we'll call it R1 cis theta 1. Okay, you don't need to write this, but I'm just trying to explain it on. Now, R is the square root, the magnitude of 1 squared plus minus root 3 squared. Okay, so that's the distance here from the pole. Okay, this is the pole here, and it's that distance there. Now that distance is just simply 2. Okay, so that's 2, and what we're going to have is that's 2, and then we've got to find our reference angle. Now, as you can see there, that angle there, theta 1, is equal to, well, that's equal to the inverse tan of the y component over the x component. Let's just do that as root 3 over 1, and we'll just worry about what quadrant it's in later. So what's inverse tan of root 3? Pi on 3. Okay, pi on 3, good. Now, just so you know though, pi on 3, but that's in the second quadrant, so it's pi minus pi on 3, which is 2 pi on 3, isn't it? Wow, no, sorry, sorry, over here, that's minus pi on 3. Fourth quadrant, my bad. So that's 2 cis of minus pi on 3. You don't have to do all of that work, trust me. You can basically go from here straight to here if you like. But knowing what quadrant it is very important. Now, and the next thing I'm going to do is I'm going to write minus 1 plus I and is equal to. Now, I'm doing the magnitude of that, which is root 2. And as you can see, the angle in there, that reference angle in here is going to be pi on 4, isn't it? That one's a nice and easy one, inverse tan of 1 or negative 1. So what we've got is that's going to be cis of, we're over here, so that's going to be 4 pi on 4 minus pi on 4, 3 pi on 4. Okay, so now what we can say is, therefore, 1 minus root 3i over minus 1 plus I is equal to 2 cis of minus pi on 3 divided by root 2 cis of 3 pi on 4. Now, when you go ahead and do those, it's just straight off your formula sheet. What I'm doing is I'm dividing by, if I had this as Z1 and this was Z2, I'm actually just dividing the modulus, and I'm then subtracting the denominator, that argument from the other. So that is equal to 2 over root 2 cis of minus pi on 3 minus 3 pi on 4. Now it's just asking for the principal argument of Z. Okay, so the principal argument of Z is just the angle. Okay, but it's the angle that's actually in our range that we've looked at. So that's equal to 2 on root 2 cis of, now let's get it, that's going to be on 12, so that's going to be minus 4 pi on 12 minus 9 pi on 12 which is equal to 2 on root 2 cis of minus 13 pi on 12. Now, is the answer, what is the answer? Is it minus 13 pi on 12? No, because on your formula sheet and for specialist maths, argz is between pi and negative pi, non-inclusive of negative pi. So therefore, what we're going to say is the answer, you don't have to write answer, but the answer is that arg of z is equal to, we need to add or subtract any value of 2 pi. So I'm going to add 24 pi on 12 to that, which is going to be 11 pi on 12. So your answer there is 24, 13 is argz is 11 pi on 12. Done. Now, we probably, once we do that, we could have done that in about 3 minutes, tops. Okay? So I'm going to just quickly, let's have a look at this one. In this case, you can see now, this is actually taken from an exam too. And this is the easiest 3 marks you'll ever get. You'll need to find this question. It's not next to it. Okay? So, first of all, it says, given that z is equal to 1 plus I. Now, the moment you see that we're squaring it and 2 to the power of 4 and so on and so forth, you really need to convert to polar form. So 1 plus I is equal to root 2 cis of pi on 4. You should be able to recognise that straight away. The modulus is 2, root 2, and the angle is pi on 4. Now also, root 2 is going to be somewhere in here for z. Can you see there that if this is 1 and this is 2, root 2 is about 1.42 or something like that. So root 2, z is going to be somewhere in there. Okay, somewhere in there. 1 plus I, in actual fact, there you go. If you go across 1 plus I, that's going to be z right there. Can you see that? So you need to be very careful with these because this is the easiest marks you'll ever get. But you'll be surprised how many students get it wrong. Now, z squared, well, let's not deal in Cartesian. Let's deal in polar form. So if I've got root 2 cis of pi on 4, we can use Demoivres' theorem. And that is, Demoivres' theorem basically states, which you should have in your notes, if z is equal to r cis theta, then z to the power of n is equal to r to the power of n cis of n theta. All it is the law that you already have. Let's think about z. If z is r cis theta, what about if I did z squared? Z squared is equal to z times z, which is equal to r cis theta times r cis theta, and that's equal to r squared. And then what are we doing to the angles? Theta plus theta. Okay? So as you can see there, that we're actually just bringing that power in and multiplying the angle by the power. Okay? And then, of course, the number, of course, is to the power as well. That's where it really comes from. And that's also in your notes. Now, z squared. So let's get back to this. Z squared is equal to root 2 squared is 2. And cis pi on 4 times 2 is cis of pi on 4 times 2, which is pi on 2. 2 cis of pi on 2. Now, 2 cis of pi on 2, that's easy because we've got a distance of 2 from the pole is pi on 2. 2 cis of pi on 2 is actually the same as 2i, isn't it? If you wanted to convert it back. But there you go. There's z squared. Now, z to the power of 4. You could actually do a few things. You could actually square that if you wanted to. That would probably be the easiest way to do it. But if you wanted to do it back over here, root 2 cis on pi on 4 to the power of 4 is equal to root 2 times root 2 is 2 times root 2 is 2 root 2, 4. Yeah, so that's 4 cis of what? Of pi. Okay, 4 cis of pi, which does exist. And of course, cis of pi that's the same as negative 4, isn't it? Or you could have done it this way. Yes, you're right. If you just had something simple like 2i and you had to square it, 2i squared, that's when I'd be using Cartesian form. Okay, that's 4i squared, which, surprise, surprise, is -4. Okay, so there you go. There is the easiest 3 marks you'll ever get. You don't need to explain it to anyone when you're doing it. You could literally do those 3 marks in 45 seconds. Okay, when you're really up to speed. So, as I can say, it's very useful to convert things from Cartesian to polar, especially when you're dealing with powers and things. Now, let's have a look at this one together. I'm going to do one in the whiteboard with you guys and girls in a second. But this one, it says verify that root 3 on 2 plus a half I is one root of the equation. So what we're going to say, if that's a root, then what we're going to do is, let's get that, and we're going to do it to the power of 3. But before we do it, what are we going to do? We're going to convert to polar form. That's correct. Now, let's do it. I'm going to do it in one step this time. It's the square root of 3 on 2 squared plus a half squared. Okay, and then we've got cis of a half divided by root 3 on 2. That's 1 over root 3. So my reference angle is going to be pi on 6. So it needs to happen that fast. You don't get any extra working for doing it on the side. If you go straight to the answer, that is perfectly fine. It's in the first quadrant. Okay, now we've got root 3, that's 3, 4, 4 over 4, that's 1. So isn't it just cis of pi on 6? Yeah? Now, if I got cis, so what we're going to do is cis pi on 6. If I did cis of pi on 6, and I did that cubed, what's that going to give us? That's going to give us cis of 3 pi on 6 using our Demoivres theorem. We don't have to write that we're using Demoivres theorem. They know what we're using. And that's equal to cis of pi, that's equal to cis of pi on 2, which is equal to I. Verify as required. Can you see there that we've verified that? All right, so we don't have to go anymore. And look, some of these questions can be a bit strange. 1 mark for that. I guess it's 1 mark because you've already been given the answer, and sometimes that does take, sometimes these 1 markers, they can seem a little bit unfair, but you're certainly going to have questions like that 3 marker we just saw before that you could do in 45 seconds. So sometimes you just have to suck it up, and in this case, they want you to have that because you're going to need that answer for later. So, yeah, this is one of those things that probably will take you a minute and a half to do that, Mark. Now, it's asking us to plot the 3 roots. Now, just so you know, the 3 roots, first of all, one of those roots is I. Okay, so one of those roots is I. This is 1 root. Okay, so this is I. Now, the question is, this is where it, I guess we're going to look at these things later, but what happens is the roots of an equation are actually spaced evenly around the Nargan diagram. They're spaced evenly around. So given that fact, and we will spend more time on this next week, but where are those going to be? If we've got 3 roots and we've got 360 degrees in a circle, they have to be separated by how many degrees? 120. Yeah, so as you can see, I'm going to go around here and another 30 degrees there. There you go. That must be another root as well. Plot the 3 roots of I. So this is z cubed is equal to I. Okay, sorry. We've got okay, my apologies. We've got one of the roots over here was verify that is one of the roots. Okay, so one of the roots over here is root 3 on 2 plus I. Root 3 on 2 plus I. Where would that go? Didn't we say that it was over here? Pi on 6. Okay, so that's 1 root. Let's call that Z1. Okay. So my apologies. Getting back to that. what are so where are the other three roots? They're separated by 120 degrees. Okay, so we've got 60. So there you go. There's going to be, we could call that Z1. There's going to be another one here, isn't there? Okay, yeah, just one sec. So just to recap, I wasn't going crazy. The three roots of an equation, when I have, in this case, if I have Z cubed is equal to I, then the three roots, we could call them Z1, Z2, and Z3. The three roots which solves this equation are going to be equally spaced, okay? And they're going to be the same distance from the pole. So there's our three roots there. Another easy 2 marks, okay? So the confusion was the conjugate root theorem, okay? So we're going to talk about that in more detail later, absolutely, when we're solving in 4E. Okay, let's do this on the whiteboard. I'm going to pause this and we're going to go through this in a moment, but we're going to give you, say, 5-6 minutes to do this. So let me pause this, and if you're watching this video and you're in November and you're trying to teach yourself complex numbers again, you can pause it now and try this one. So, first of all, now, shh. Okay, so I've got my stopwatch on and we're going to have a go at this. So this is what you'll need to do. This is how you would do this in the exam. I would go straight to this, and I'm thinking in my head, 2 times 2 is 4, and root 3 times root 3 is 3. So that's going to be the square root of 12 plus 4 cis of pi on 6. You could do that straight away, no problem. If you're making mistakes, please draw an arcane diagram. And so that's equal to 4 cis of pi on 6. The next thing is 1 minus root 3i. That is equal to, now automatically, square root of 1 squared plus root 3 squared is the square root of 4, which is 2. Cis, inverse tan of root 3 is pi on 3, isn't it? But we're in the fourth quadrant. So that's, what is it? We're looking at minus pi on 3. Now, therefore, you need to write this out, please. A lot of students are not doing this. 2 root 3 plus 2i, 1 minus root 3i is therefore equal to 4 cis of pi on 6 divided by 2 cis of minus pi on 3. Now we apply that. That's 2 cis of pi on 6 minus pi on 3, or plus pi on 3 minus negative pi on 3, which is equal to 2 cis of 3 pi on 6, which is 2 cis of pi over 2. Now, I was explaining that to you, and that took me 1 minute and 48 seconds. So I reckon you could do that much sooner. About 1.5 minutes you could probably do it in. And I think the average was quite high for that. I think the average was, were you saying, Jack, 3.1 out of 4. First question tends to be fairly easy. Most exams, not guaranteed. Okay, now let's get back to this. Now, before you know it, now this is interesting, this one. We just had a bit of a debacle about the whole conjugate root theorem. Now, in actual fact, can anyone, let's talk about this just now. Z to the power of 8 equals 1. Are all the coefficients of this real? Yes. So what do they come in conjugate? The solutions will come in conjugate pairs, but in actual fact, there's 8 solutions. Okay, Z to the power of 8, the fundamental theorem of algebra. Let's do this really quickly together. Z to the power of 8 equals 1. Now, what I'm going to do is I'm going to change 1 to polar form. What is 1 in polar form? What is 1 in polar form? Cis of what? 0. Okay, this here is cis of 0. Now, what we want to do, though, is you can see there, if I've got Z to the power of 8, then what we have there is cis of 0. Now, I want to then find, it says here plot the roots. Now the roots are the solutions, okay? But the interesting thing here is that I'm going to change this 0 because this 0 can be quite a few things. I can add or subtract. I'm going to show you a bit of a trick here, which is we're going to spend more, we can add 2k pi. I'm going to call that 0 plus 2k pi. By the way, this is actually from 4H. I think it's 4H or G or something like that. So let's change that to Z. Now let's apply the Demoivres theorem now. Okay, let's apply Demoivres theorem. So Demoivres theorem means that if I want to find Z, then what I can do is that Z is equal to, I'm going to do that to the power of 1/8. 0 plus 2k pi to the power of 1/8. Now, just so you know, K, what do you think K is? K is what? Is it whole numbers? Is it they're whole numbers, but can it be negative as well? So what do we know as positive and negative whole numbers? We know that as what? Starts with I. Integers and what is integers? That's the notation for integers. Okay, so what does that mean? Z can be -1, -2, -3, 0 as an integer, 1, 2, 3, and all that sort of thing. Yeah. So let's apply Demoivres theorem here. When I do to the power of 8, well, that's easy because 1 to the power of 1/8 is just 1/8. Oh, sorry, is just 1. Okay, but what are we doing to the power? 0 plus 2k what? Pi on 8. Look at that. Isn't that awesome? Now, that's going to be cis of what we're going to do. That's going to be 2k pi on 8, which is k pi over 4. Now, what we can say is we can say that k could equal 1, couldn't it? K could equal 2. K could equal 3. Could it equal 4? Yes, it could. Could it equal 5? Are you sure? Well, if 5 pi and 4 technically would go the other way. Okay, so we could equal, K would equal -1. K could equal -2. K could equal -3, but can it equal -4? No, because, well, so K could also be equal to what? 0. Now, if K is 0, cis is 0 is just there. Okay, good. Now, what do we talk about these roots? There's 8 roots and they are equally spaced. They are equally spaced. So, if they're equally spaced, 360 degrees divided by 8. Isn't that 45? So, as you can see there, there's another root. There's another root. There's another root. There's another one. 1, 2, 3, 4, 5, 6, 7, 8. There's our 8 roots, and they are equally part. You don't need to label them or anything like that. It's just we've plotted the 7 roots, and as you can see there, this is for different values of k, basically. And look at this. What do you notice about these two? What do you notice about these 2 points? What do you notice about these 2 points? What do you notice about these 2 points? They are the what of each other? They are the conjugate. And the reason why they are the conjugate is due to the fact is the conjugate root theorem, which isn't very obvious necessarily all the time. But as you can see over here, the coefficients are real. So if the coefficients are real, therefore, they're going to come in conjugate pairs, which you can see here. In actual fact, there's 4 pairs of conjugate pairs in this case. If we have a cubic, you can't have 2 pairs. You'll have 1 pair of conjugate and you might have another solution as well. All right, but that other solution might have to be real. Okay, now I'm going to just pause this here and, well, we can do this. Did I say we could do that on the whiteboard? We're going to do this on the whiteboard here. So I'm going to pause this. In actual fact, I'm going to stop this video here because we've got 7 minutes of class. But what I'd like you to do is have a go at that sort of thing and apply the same thing. First of all, if you've got this, then u to the 6, change this to polar form. Okay, if you had this to polar form, then u to the power of 6 is quite easy to manipulate. Now, if you wanted to find the roots, then what you'd have to do is you'd have to do u is equal to like u to the power of 6 to the power of 1/6, if you like. And we're finding the roots using Demoivres' theorem. Now, I'm going to stop this video here. Hopefully you've picked up something today.